All right, next I'd like to look at a special case of our relationships between displacement, velocity, and acceleration that involves a constant acceleration process. Why do we want to do this kind of a special case? Because it is so applicable to many things around us. For example, just following the motion of objects either in 1D or in 2D. We are dealing with problems that involve constant acceleration. And so the math is a little easier than what we did in that last example where the acceleration varied with time. And it also is very practical in that we can look at many aspects of motion as being constant acceleration processes. Now, if we're dealing with something that's constant acceleration, we're usually not considering things like air resistance if this is a motion problem. And so we're dealing with problems in which the velocities are slow enough so that there aren't any significant impediments to the motion that are caused by friction due to the air. Okay, and so if we are dealing with a constant acceleration process, that is often referred to as being related to our kinematics equations. We have the relationship of acceleration being derivative of velocity with respect to time, but that's also delta v over delta t if and only if the acceleration is a constant, i.e. the velocity versus time plot is rise over run, and it's a straight line plot. So this would be delta v, and that would be v final minus v initial. What's v final? Well, it's just the velocity at some time t. So if I call this time here t, then v final is the velocity at time t, and v initial is the velocity at t equals 0. Now what do I mean by time t? Well, I mean that any time that I want, which is the time elapsed since time equals 0, could be plugged in for the time. Okay, and then on this horizontal, this is rise over run, so this would be delta t equals t final minus t initial, or we could just write that as t. So in other words, delta v over delta t could just be written here as v final minus v initial divided by delta t, but that's just the final time minus 0 if we're defining the initial time to be t equals 0. And so this gives us our first relationship, which is a collection of these algebraic expressions that relate velocity, displacement, acceleration, and time to each other. And so this gives us then A equals v final minus v initial over t. And I'm putting little arrows over the vectors to remind us that we are dealing with vector addition and the processes that relate to vectors. So if I solve this algebraically for v final, we get v final equals v initial plus acceleration times time. So this is what I'll call kinematics equation number 1. And my goal here is to find a whole collection of these kinematics equations that relate different combinations of the physical quantities to each other. So we have our choice. We can pick whichever equation we want to solve for the desired result. All right, so the next equation that I wanted to look at, equation 2, we can get from the fact that since this is a constant acceleration process, if it's traveling some initial velocity, there's some acceleration acting, then it's the velocity is going to change. It's either going to get bigger or smaller, depending on whether the acceleration is pointing in the direction of the velocity vector or pointing in the opposite direction from the velocity vector. So again, what I'm trying to represent here is, let's say with this air cart, we can see which way it tends to go, so I know the acceleration is going to be this way. So if it has some initial velocity, then it's going to be picking up speed. At this point it has an initial velocity, but then it's going to get going even faster to its final velocity. And associated with that then, it's going to traverse some distance, x. So in this next example, basically what I want to do is just use the fact that average velocity times time equals distance. So distance then, or our displacement vector, is going to be equal to average velocity times the time over which the acceleration is acting. Okay, so the acceleration is causing the velocity to change at a uniform rate. So again, we can look at the velocity versus time plot. You can see that we go from v0 to v final. So it's a straight line plot. And so v average is just that point in the middle, which is equal to essentially 1/2 times v0 plus v final. Okay. And so in other words, if v initial, let's say, were 10 meters per second, v final were 20 meters per second, then we could pretend that all of the motion was at a single velocity, which is the average value of 15 meters per second. Okay, but that would only work as long as the velocity were increasing linearly. If this were a parabolic function, then the average value of that function would be much more difficult to calculate. Okay, and so here, this is only working then for a constant acceleration process. So if I plug in for average velocity then, just 1/2 times v0 plus v final times t, then that becomes the second of my four kinematics relationships. Okay, this one involves v final, v initial, a, and t, and so there's no x displacement in this one. So what we're looking at then are relationships between these four vector quantities and the scalar quantity. And this one has everything except for the displacement, which could also be labeled as a y if we were talking about one-dimensional vertical motion. And then this equation has no a in it. Okay, and so let's see if we can eliminate some variables and find some other relationships where the equations have all but one of the unknowns in it. For the next example, what I'd like to do is take the expression here for x and plug the expression from equation 1 in for v final there. Okay, and so if I do that, it gives me x equals 1/2 times v0 plus, and then for v final, I'll write v0 plus at. And then I'll multiply that all by t, then that'll give me x is equal to v0 t, because here we have 2v naught times 1/2 times t, and then 1/2 at times t is 1/2 at squared. So that then becomes equation 3. And so this one has no what? Can you see which of these 5 it doesn't have? It's v final. Did you get that? Okay, so that is what equation 3 doesn't have, is v final. So when would we use equation 3? Well, when we don't know what v final is and when we don't care, when we're not asked for it. Then why would we want to mess with v final if we're not asked for it and we're not given it? And so this just gives us a way of identifying which equation gives us the right answer with the minimum amount of calculation. So that's equation 3. Then finally, we'll have one more of these, equation 4. For this one, I'd like to eliminate the time so that the fourth equation won't have time in it. And I can do that again by taking this expression for equation 1 and solving it for the time. So I can do that here. The time from equation 1 is just v final minus v initial over a, and then plug that into equation 2 for the time. So that'll give me x equals 1/2 times v0 plus v final times the time, which is v final minus v initial over a. Okay, and then I have the sum and the difference here. It's like x plus y and x minus y. That would be x squared minus y squared. So here we can write this as v final squared minus v initial squared over 2a. Okay, so that's just the sum and the difference is the difference in the squares. And then the 2 and the a go down to the bottom. And so equation 4 then is going to just be v final squared equals v0 squared plus 2ax. And so with just a little bit of algebra then, and the knowledge of rate times time equals distance using the average velocity and the definition for constant acceleration, we are able to fairly quickly get a set of 4 equations that have different combinations of unknowns within them. So the next step then, and we can look at the data projector for a moment to see how this would work, is we can look at these equations. This is the first one. Now here we're using bold lettering to indicate vectors rather than having the arrow over the quantity. And here's our net displacement vector, which is x final minus x initial. That's what we're calling x here. That's our total displacement. And so if we have that combination of problems, then here is a set of steps for the solution to a problem that involves constant acceleration. Step 1, draw a clearly labeled vector diagram, choose a positive direction, and make sure the units are in meters, kilograms, seconds. Step 2, identify known and unknown quantities, v final, v initial, a and t, and x. And you need to know 3 out of 5 of these to continue. Then eliminate all equations involving the unknowns that are not asked for or needed in the problem. And then finally solve the remaining equation for the desired answer. Okay, so those are our equations. And so let's do that with an example. In this example, let's say that we have a fan cart, and that fan cart is moving with an initial velocity of 10 meters per second at time equals 0. Okay. And then, as time goes on, we eventually reach a point where the final velocity is equal to 20 meters per second. And let's furthermore say that the time that it takes for this to happen is 5 seconds. So it starts from 10, increases its velocity to 20 over a time period of 5 seconds. So that is our time elapsed. Let's find the distance traveled. Here we're assuming the acceleration is a constant. So that's just like our fan cart here. Let's look at our fan cart again. The fan cart is moving, and right there we start. Right there, so it's moving at a certain initial speed, then we let it go for 5 seconds. We stop the stopwatch. It says 5 seconds. We measure the final velocity, and we want to know, well, how much table did it take up? And we're not told what the acceleration is. Okay, so that means that, you know, if we're thinking carefully about this, we might be able to go back to our kinematics equations and find an equation that doesn't have the acceleration in it. And that might be the one that would give us the correct answer. Okay, so what do we do first? Well, in step 1, we draw a clearly labeled diagram. Now here I'm going to want to draw the x displacement vector in my diagram. And I also, even though I haven't been told what the acceleration is, I know that the acceleration must be pointing in the same direction as the velocity vector, or else the object wouldn't be speeding up, right? It would be slowing down if the acceleration were pointing in the opposite direction from the direction of the velocity. So even though I don't know what the acceleration is, a complete vector diagram would include an acceleration vector that points in the positive x direction. All right. And we also want to define what we mean by our positive direction. Okay, and so the positive direction, then, positive x should be to the right, because that's the direction that everything is moving. And so if I define positive to be to the left, then everything would be negative. It might still be able to get the right answer, but it would be harder, because we would be choosing an unnatural positive direction. Okay, so this is step 1. And I also, in step 1, if this say we're in kilometers per hour, I'd want to convert that to meters per second before I even get started with this problem. So that is what we meant in that original statement where we said make sure that the units are meter, kilogram, and seconds. Then in step 2, as you can see, and I, by the way, have I've put all of these slides up on Canvas for you, so you can refer to these as you're going through the lecture. We want to identify what it is that we know and what don't we know. And so I really do recommend that you set up a table. And so this is the kind of table that I am going to set up for this, that I hope you'll do it the same way. This just keeps your thinking organized, and it allows you to go through and solve the problem essentially the same way each time, which a lot of people like because it gives you a feeling of confidence to know that you know what to do on a problem and that you're not just going to be confused and not know which way to start. All right, so our known quantities are, out of those 5 quantities, we know V naught is 10 meters per second. we know v final is 20 meters per second. We know the time is 5 seconds. The unknown quantities are the acceleration, so put a question mark in for that, and x. We don't know what that is either. Now, what we wanted here was x. So how do we find x? Well, in step 3, it tells us to eliminate all of the kinematics equations involving the unknown that's not asked for. Okay, so I go through and I go, well, which one's not asked for and isn't needed in the problem? The answer is the acceleration. I don't care what it is because I wasn't asked for it. And I wasn't given any information about it in the statement of the problem either. And so I can go to my 4 equations. I can say, well, no, this one's got an A in it. Get rid of that one. This one's got an A. Get rid of that one. This one's got an A. Get rid of that one. But look at here. This is the one. That's the one that we want. Now, a lot of people, what I've seen in the past when I've helped people solve these problems, is that they just want to react to the problem and just pick an equation. This one, I kind of feeling like I want to pick this equation. Now, if you go to Las Vegas and each time you go to Las Vegas, you win because you're so incredibly lucky, then you can just randomly choose whichever one of these equations you want, and you'll always get it right. Okay? But if you have normal luck, like the rest of us, then it might be nice to have a system for finding which of these equations will get you to the right answer with a minimum amount of work. And so it's this one here, because this one doesn't have an A in it, and we don't care what A is because it wasn't asked for, it wasn't given in the problem. Okay, so that is the one. So we'll choose that equation. Then x is going to be 1/2 times v initial, 10 meters per second, plus v final, 20 meters per second, times t, 5 seconds. And so that'll give us 20, 10 is 30, divided by 2 is 15, times 5. That'd be 75 meters. So that's how far we would move then in 5 seconds under the influence of this constant acceleration. Okay, and so now let's say that we do want the acceleration. Now that we found the displacement in part B, let's also find the acceleration. How would we do that? Well, now in our known-unknown column, we can proudly put the x displacement as a known quantity, 75 meters. And then we can use whatever equation we want to solve for A, because now we know 4 out of 5. Okay, when you know 3 out of 5, then you've got to go through and figure out which equation to use. But when you know 4 out of 5, you can choose any equation you want as long as it's got A in it. So, interestingly, the only one that we can't use is equation 2, which we used for part A, because that one doesn't have the acceleration in it. But we can choose any of the other ones, because all the rest of them do have acceleration in it. And so, with this huge choice of possibilities, which one do I pick? Well, I mean, you could pick this one, but it's a little more algebraic to solve for A. Same thing with this one. But this one looks like the easiest one to me. So if you solve this one for A, what you get then is just A is equal to V final minus V initial divided by the time. And so that's just V final was 20 meters per second minus V initial, 10 meters per second, divided by 5 seconds. So the acceleration is just 10 divided by 5, 10 meters per second divided by 5 seconds, or 2 meters per second every second, which is the same as 2 meters per second squared. Okay, now, if we know enough about acceleration, we can actually work this through in our heads to see that that value for the acceleration is consistent with what we've solved for so far. Remember that we started with an object that was moving at 10 meters per second at time equals 0, and then we finished up at time equals 5 with a v final of 20 meters per second. So in the first second, we're going to go from 10 to 12, if it's 2 meters per second squared. In the second second, 12 to 14, and to 16 in the third second, to 18 meters per second in the fourth second, and then to 20 meters per second at the end of the fifth second. So yeah, it all makes sense. And so you don't necessarily just have to go through and hope that you chose the right equation and then you're kind of covering your eyes so that you don't have to see whether it's wrong or not. You can go through and make sense out of your result. And if you understand what's going on in the problem, you understand what the basic definition is for a constant acceleration, that the velocity increases uniformly, then you can check your answer and make sure that your answer is reasonable. Okay, so let's look at another kind of problem. In this one, let's look at a gravity problem. In this gravity problem, let's say that I start out with an initial velocity of 50 meters per second in the vertical direction. And this is under the influence of gravity. And so the acceleration then we could write as minus 10 meters per second squared, because we know the object will first be slowing in the positive direction and then speeding in the negative. I can then define a positive direction as being up. And the only thing I have to do with these equations is change the x's to y's. I don't have to do that. I could just define vertical as x, but it's more conventional to call it y. Okay, so now this also works for our vertical equations as well. So in this problem then, with an initial velocity of 50, let's find A, the maximum height the object reaches. B, let's find the time to the maximum height. And C, let's find the velocity at t equals 7 seconds. And also at 10 seconds. All right, so in part A, let's do this one at a time. We know what the initial velocity is, 50. We know the acceleration. And in part A, we're trying to find the maximum height that the object reaches. So let's put those two down. V naught is 50 meters per second. The acceleration is minus 10 because it's pointed in the down direction, which is in the opposite direction from the direction of the motion, at least the initial motion of the object. So it looks like we only have 2 out of the 5. And we need 3 out of the 5 to go farther. Here there's a hidden piece of information in the fact that we're talking about the maximum height. And so even though it is not explicitly stated in this problem, you would need to be able to deduce that the maximum height occurs when the final velocity at that maximum height is 0. Okay, and so that is a piece of information that goes in. You say, well, what good is it if it's 0? Well, that's just fine. That's an important piece of information. If it's 0 or some non-zero value, that still is a known quantity. And so that goes in there. And that gives us 3 out of 5. Then our unknown quantities are the maximum height, y, and the time of flight, t. Okay, and so what I want to do next then, since we're asked for the maximum height, is we'll get rid of all of the equations involving the t. That's again step 3. Okay, in step 3, you get rid of all of the kinematics equations that involve the unknown that's not asked for. Okay, and the unknown, in this case, that's not asked for in part A is t. You might say, well, wait a minute, it is asked for in part B. But yeah, we're only doing one at a time, though. So while we're doing A, the time is not asked for yet. So that means that we can get rid of all these equations that have the time in it. That gets rid of equations 1, 2, and 3, and leaves us with equation 4. So this is almost too good to be true. We can just, by a simple process of elimination, decide which of these 4 equations we need in order to solve for the maximum height. So we'll write this down then. V final squared equals V0 squared plus 2AY. Now A here is minus 10. But one word of caution. If you write A is minus G and then write G is minus 9.8 or minus 10, then you're making it positive. And gravity is not positive here. It's slowing you down in the positive direction. So just put in the 1 minus sign and don't try to think ahead and say, well, G is negative and A is minus G, because then you'll make a minus sign here. Just put in that it's minus 10, and that takes care of it for you. All right, so V final squared is 0. V initial squared is 50. Should probably put in the units in this first step. Plus 2 times the acceleration. Now you plug in the minus 10 times y. So y then is your unknown quantity. Okay. And so this is minus 10 meters per second squared. So in the first step, it's good to put in all your units. But then in subsequent steps, the units probably just get in the way of you solving the problem. And so I would leave them out in the subsequent steps. So here we have 2 times 10 times y. I'll bring that over to the other side. So that's 20y equals, and then here, 50 squared is 2,500. So 20y equals 2,500, or y equals 2,500 divided by 20, and that would be in meters. So 2,500 divided by 10 would be 250. So divided by 20, that would be 125 meters. So that would be our value for y. Now, is this exact? The answer is no, it's not exact, because the actual acceleration due to gravity is minus 9.8. Okay, and we put it minus 10. So I'm doing this to make these examples go faster for you, but as you get to the mastering physics problems, be sure to put in the 9.8. And in any lab problem, put in the 9.8 too. On an exam, either one is acceptable. In mastering physics, they only allow for like a 3% error at the most, 2 or 3%. So if you're putting in a 9.8 as a 10, that's already 2% error right there, right off the top. So you're right near the edge of the tolerance for accuracy with significant figures. And so be sure that for any non-test quiz exam type of situation that you plug in, that the acceleration is 9.8. Okay, so that gets us through the first part of the problem, and we now know what y is. Now in the second part, we want the time to the maximum height. So I can revise my known unknown table and write here y is 125 meters. And then we'll solve for the time to the maximum height. Okay, so which one should I use? Well, usually when I have a choice, I did this last time, and I'm going to do it this time too. I'm going to choose the first equation because it's the least algebraically complicated of the four. Okay, and that's the only reason. I could choose any of the other ones that have time in it too. But this one would be, I shouldn't say a dumb equation to use, but it sure is creating a lot more trouble than it needs to solve a quadratic equation for the time when you've got two other equations that give you a relatively simple solution that doesn't involve the quadratic. So I'm not saying be afraid of the quadratic equation. If you have to use it, but don't use it if you don't need to because you'll save time and there'll be less chance of you making an error if you have less computations to do. All right, so this is A then. In part B, we're going to choose this equation for the time, solve that for the time. So T then is V final minus V initial over the acceleration. Okay, V final is 0, so that's 0 minus 50 meters per second divided by minus 10 meters per second squared. Okay, so you can see that if you got one of these minus signs wrong, then you could get a negative time. But we know that time starts from t equals 0 and moves on. So here, this would be minus 50 divided by minus 10, or plus 5 seconds. So that's how much time elapses. Now, we might ask ourselves, is this a reasonable answer? Well, here, on our picture, let's draw this as y max, and this is v final equals 0. Okay. So 50 meters per second. After 1 second, we're going to go 40. After 2 seconds, 30. After 3 seconds, 20. After 4 seconds, 10. 5 seconds, 0. So just from our basic definition of acceleration, and knowing that we're slowing at a rate of 10 meters per second every second, this is a reasonable answer for the time. Okay, so that's part B. Part C, let's find the velocity at t equals 7 and 10 seconds. Okay, so now we know all of these, and so we might as well use an equation that involves the velocity that is most straightforward in terms of the algebra. So that's equation 1 again. So v of 7 is just v of t at t equals 7 seconds. Okay, so I'm not saying v times 7. I'm saying that it's a function of time at t equals 7 seconds. And so v of t in general is v0 plus at. And so v of 7 then is going to be 50 meters per second plus minus 10 meters per second squared times 7 seconds. Or that's 50 minus 70 is minus 20 meters per second. Okay, so if after 5 seconds we get to 0 velocity, then in the 6th second, we're going to be going minus 10. In the 7th second, we're going to be going minus 20. Okay, so that's just, we're speeding up now in the negative direction, and that's minus 20. So therefore, v of 10 would be 50 meters per second minus 10 meters per second squared times 10 seconds. So that would be 50 minus 100, or minus 50 meters per second. So do you see here that v of 10, or v final at t equals 10 seconds, is the negative of the velocity when it started. So v of 10 is v final for this case when t equals 10 seconds is minus 50 meters per second. And so this is true in general then. If you throw an object up into the air and then you catch it again at the same height from which it is released, it's going to be moving the same speed in the down direction as it was moving up, because it's an exactly symmetric problem in which the amount that it slows down on the way up equals the amount that it speeds back up on the way